Log on, tune in, find out. Another good idea from Cambridge.
So we continue with Daniel.
Okay, so today I'll actually define what a stability condition is and then kind of classify them in the case of curves. But let me recall what we finish my talk from yesterday. Yesterday I talked about two things and which are kind of analogous, namely torsion theories for an abelian category. And the torsion theory in an abelian category consisted of two additive subcategories, T and F, satisfying two properties, namely that there are no, so these are full additive subcategories, there are no morphisms from T to F, and for any object in my abelian category there exists a short exact sequence where the first one is torsion, so in T, and the second one is torsion free, and so an object in F. And the analogous notion for a triangulated category was, so D, a triangulated category, T structure, and the T structure was also given by two full additive subcategories. I started to call them T and F, but to avoid confusions I call them right away D smaller or equal to 0 and D positive. So again, full additive subcategories satisfying similar conditions, so such that again there are no morphisms from the torsion part, so this is this one. Then I replace short exact sequences by triangles, so for any object in the exists an exact triangle where the first one is in D smaller or equal to 0 and the other one in D positive. And now there's a third condition because there's one additional structure, namely I want that this category, which is so D smaller or equal to -1, which by definition is the shifted category D smaller or equal to 0, I want this to be contained in the original one. Okay, and there was yesterday in the tutorial there was a question, and this is an exercise which I'll need later, namely to decide when I should say one further thing. So for any T structure on a triangulated category, there's an abelian category, which is called the heart. And yesterday there was this question, can I decide if I give myself an abelian category or an additive category in D when it is the heart of the T structure? And in fact there is an exercise that can be done. So if A is a full additive subcategory of a triangulated category D, then A is the heart of a bounded T structure if and only if for each object E in D there exists a kind of filtration. So filtration in the usual sense doesn't make any sense because we don't have any sub-objects in derived categories. So instead we say for all E and D there exists a sequence of distinguished triangles so these are exact triangles, and that means the morphism from A1 to and from A2 to A1 are all of degree 1. And this is a finite diagram ending with En equals E, such that the objects, the cones of these morphisms here, these AIs, are shifted objects in the category A. So such that AI are objects in the shifted category, shifted by ki, and the shifts satisfy this condition, so the shifts are strictly decreasing. Right. So yeah, that's a description of all the hearts that can occur. In particular, this full additive subcategory is then an abelian, even if you didn't assume it. Okay. So now I want to put these two things together, and so this is part 4 of yesterday's talk. So I want to talk about combining these two notions, torsion theories and T structures. And I start with an abelian category as before, and I look at the bounded derived category of A. The abelian category sits as a full subcategory in the derived category. It's actually the heart of the standard T structure. And if I give myself now a torsion theory for this A, I can define a new T structure on this derived category. So if Tf is a torsion theory in A, then one defines A sharp. So this is the tilt of A with respect to this torsion theory. This is the full additive subcategory of my triangulated category, consisting of all objects E. So these are now complexes with objects in A, such that the cohomology is concentrated in degree 0 and -1 if I is not 0 or -1, and in degree 0 the cohomology, so this is an object in A, I want this to be contained in T, and in degree -1 I want it to be contained in F. This is the tilt of the category A with respect to the torsion theory Tf. Okay, and now the exercise 2, so this was exercise 1, which you can do by actually applying exercise 2, is a result of Happel, Reiten, and Smalow. This tilt, this abelian category, is again the heart of a bounded T structure on this category. Then A sharp is the heart of a bounded T structure on dBA. In particular, this A sharp is abelian. Yes?
In the same triangulated category set a bunch of different T structures with the same heart, or is that?
No, the heart determines the T structure uniquely. The same thing works if, so here I take like the abelian category, it's bounded derived category, and view the abelian category as the heart of the standard T structure. You can, in fact, for this, you can take any triangulated category and A the heart of a bounded T structure on this triangulated category. So it works as well for A the heart of any bounded T structure. On a triangulated category. In exercise 1? That's true. Yes, thank you. I need thank you. Okay. So now in the example, the motivating example from yesterday, I started with the abelian category of coherent sheaves on a smooth projective curve. And then we have defined these subcategories of semi-stable sheaves, and under the stability function, the only one we have seen so far, minus degree plus I times the rank, I get these rays for the various phi's. The one down here, so P1 was the subcategory of torsion sheaves. And in particular for fixed, if you pick one little phi, we have a torsion theory given by all those of with semi-stable factors of phase bigger than phi and f the remaining ones. This is a torsion theory, as I explained yesterday. This is a consequence of the Harder-Nauer-Simmer infiltration. And what we find is then that I get a sequence of abelian categories. The tildes of the original one, so of the abelian category of coherent sheaves, with respect to, let me put a little phi here to stress the dependence on the phi. So this is now a family. This is the family of Hards, or in other words, there exists a family of T structures on Co-C parametrized by the half-closed interval 0, 1. Okay, so there's the standard T structure. You can start with the standard T structure. And then you can pick a phi, and each phi gives you a family of gives you a T structure, and you should think of this as a family, like a continuous varying family of T structures on this on the triangulated category, on the derived category of coherent sheaves on the curve C. So to visualize this, you can do the following. If I still stick to my linear function minus degree plus I times the rank of E, then the image of the coherent sheaves was the upper half plane, and I had to add the negative reals. And for instance, the image this would be the image of P of A 1/2. And what else? For instance, this one, the lower half plane with the positive reals added, would be the tilde A1. Okay, this is so. What I'm drawing here is the image of these categories under the fixed stability function, under this fixed function z given by degree and rank. Okay. So any questions? So this.
You said we're supposed to think of this as a continuously varying family of T structures.
Right.
So if I take like epsilon,
Right.
where epsilon is very small, what are these coherent sheaves that are going to form the heart? I mean, you start with the ones that are actually torsion, for the case of the curve, say, and then we just turn.
Right. So that is
just a little bit.
right. So as soon as I take a very small phi, so you start with a very small phi, there will always be, no matter how small the phi is, there will always be a ray with rational slope, right? And everything that's below this thing, or it's on this thing, that gets shifted in degree -1. I mean, I haven't said what it actually means to be a continuous family, so I will have to define the notion of a topology on this thing, but I won't do this today.
So is Co-C just A0?
Say again?
Is Co-
A0 is the yeah. Yes. This is the observation I did yesterday, that the image of the coherent sheaves are in the upper half plane and the negative reals. There's nothing on the positive real axis. Okay. That's a good question. It's in general they are. So I'm sure for P1 that there are other T structures that are not of this type. I'm actually not so sure for positive genus, but the answer is yes. But we still see that these are distinguished.
I mean, the image, that plane is just the image of K, right? So could there be another heart that maps in the upper half plane?
Oh, yes. Well, first you can shift. Okay, that's for P1. Actually, I don't remember so well the construction of these exceptional T structures on P1, so I'm not sure whether those would map to the upper half plane. That's
So what you're mapping to the lower half plane are things which are actually not coherent sheaves, but in the Grothendieck group. Lower planes.
So this one?
Yeah.
Right. As you can see, I mean, as soon as something goes, as something goes to the lower half plane, its rank will be negative, or tends to be negative. So it can't be a coherent sheaf.
But it's still in the Grothendieck.
It's still in the Grothendieck group. I mean, like, because the Grothendieck group is the free abelian group generated by these things. So I can always put a -1 in front of a coherent sheaf.
Does it make sense to say that the Grothendieck group by set subjects onto C, well, to the rational points of C?
Yes, that's certainly true. Because, I mean, I always find a sheaf. I mean, I can give myself rank and degree, and I find a sheaf realizing it. So not the rational, but the integers. So the image are the Gaussian numbers, if you want. Okay. So this was my talk, the end of my talk yesterday, and I pass to my talk today, stability conditions. And so I will give definitions and examples on curves, and actually hope to classify them. Okay, so the first thing I will do, so I want to make sure that you see clearly which part of the structure of a stability condition is responsible for what. And the first thing I want to do is to introduce slicings. And slicings is a notion that refines both torsion theories and T structures, and then later we will add some more structure on it to make it actually a stability condition. So these are refinements, the torsion theories. And again, I'll try to do this for abelian categories and triangulated categories. The idea behind is a bit that somehow it's easier, of course, to work on a fixed abelian category. And very often when you do computation, somehow you try to fix first the abelian category and then look at slicings of this one. And then if you can't stay on the fixed abelian category, then you tilt and then you go to another abelian category. I'm not sure it is helpful, but I'm doing it anyway. So A is an abelian category, and D is a triangulated category. And I write the definitions both in both cases, and so you'll see from the color which one is meant. Okay, so the slicing of A respectively D is given by a collection of full additive subcategories, and in the abelian case you want the phi's to be between 0 and 1, and for the triangulated case just any real number, such that first of all So you see, it's really analogous to these other two notions. There are no morphisms from one to the other, from objects in p phi to p phi prime, if the slope phi is bigger than phi prime. The face is bigger than phi prime. Okay? And
You've written find real in red chalk, so that applies to triangulated.
that applies to the triangulated category.
What is it meant to be on just triangulated?
Well, the other one before, the thing that's written in white. So that didn't work well. Okay. And so for all objects, so this is the second condition, they exist. So I'm in the Bealing case. This is white. The filtration like this, and in the triangulated case, I have this diagram of exact triangles. So whenever you see like this, I mean, I won't write it again. This is an exact triangle in the triangulated category. So it's a finite thing such that in both cases. Say it again? It's still part of the definition of slicing. This is the second condition, but there wasn't enough space on the other black hole. So such that 1 and 2, and in both cases these AIs are objects in these given additive categories, and the sequence of phases is strictly decreasing. In both cases, the difference is that in the Bealing case the phases are between 0 and 1, and in the triangulated case there can be arbitrary reals. Okay, let me give you just two.
There's no uniqueness here.
There is uniqueness, but it's not a requirement. It's actually a consequence of 1 and 2. Okay, so let me say this first. So remark. This is what we call the Harder-Narasimhan filtration is unique. Oh yes, there's a third condition. Thank you very much. That only applies to red. Cheers.
Sorry, but so the AI in the white case are the Genius quotient?
They are what? They are?
What are the AI
Oh,
in the white case?
thank you. Yes. They are the quotients.
Why are you demanding that there exists separately in red case? Surely the morphism E1 to E2 defines uniquely A2 and things are triangulated, which completes.
I didn't get to the question. Hey.
Why are you demanding their existence separately in red chalk case?
Well, that.
Surely E1 to E2 completes the unique exact triangle.
Well, I mean, I would just want to stress the difference that here I really have a filtration by sub-objects, and here I have to use exact triangles in the triangulated case. Yeah.
If I don't want to write in white on my paper, is it going to be the case that a slicing on the abelian category, if I sort of, like, I can just promote the slicing up to the derived category of that abelian category and ask it to satisfy the red conditions?
Well, I come to this. That's a proposition. You have to say that I'll come to this. So let me first say this thing that the Harder-Narasimhan filtration is unique. And let me also point out that in this setting I cannot speak of the face of an object. I have a collection of subcategories for which the notion of the face makes sense because they're defined by this phi. But for an arbitrary object I cannot talk about the face. So if E is in P phi, then phi is the face of E, but an arbitrary object E has no face. Okay. So just two technical remarks which are useful when you compute things. For instance, if you have two objects, let's say E and B, in D or in A, so let's say in A or D, and the isomorphism from E to B, then there will be a morphism, non-trivial morphism from at least one of these factors AI to B. Then AI to B not zero for at least one AI. And the other thing which is maybe interesting is since these are not inclusions anymore, they're exact triangles, in principle you could have that the composition of E of these maps from E1 to E2 and so on to En is zero. But that doesn't happen because of the condition on the faces. So Hom A1 to E is always non-zero, as is the last morphism from E to AN. So you can check that this morphism can never be zero here, and this morphism is not zero. This is really similar to the Harder for in terms of subobjects. Of course, the composition of these inclusions is an injective morphism, so it cannot be trivial. And the quotient map from E to the quotient by En minus 1 is also non-trivial. Okay. This is this. Okay. So the thing, I mean, the idea to visualize in the abelian case is just the same. I mean, what we have seen for coherent sheaves on curves, that these subcategories are visualized by rays in the upper half plane. If I pass to the triangular setting, then all of a sudden I also get subcategories for phi prime bigger than 1. So those I can still draw as rays in the plane, but once I complete the circle, then here somehow I leave the plane. So because the phi for the triangular categories are really reals and not numbers between 0 and 2. So
the red arrows you're drawing only make sense for things in B but not in A.
that's why they're red.
Yeah.
Right. Okay, so let me give you a few examples, actually going in both ways, showing that this is really a refinement of these of the notions of torsion theory and T structure, and I'll show that torsion theories and T structures give rise to slicings, and conversely that slicings always give rise to torsion theories and T structures. So let me first start. Let this be a torsion theory in A, and just pick two numbers, phi 1 and phi 2, and define P of phi to be T for phi equals phi 1, to be F for phi equals phi 2, and to be 0 otherwise. Okay, this does define a slicing of this does define a slicing. the existence of this filtration is exactly the condition on the torsion theory to have that every object is decomposed in an object in T and in an object in F. Why I'm mentioning this example here is this is an example of a slicing where, at least in general, the p phi's are not abelian, they're just additive subcategories. So note they're only additive categories. So let's see, the analog of a torsion theory for an abelian category was a T structure on the triangulated category, so given by this subcategory, and with hard A, and we can use this to associate slicings. Again, we pick, so there we pick the two numbers, here we pick just one number, pick any phi in R, and define a slicing by saying P of phi is A shifted by, I pick phi 0, phi minus phi 0, if phi minus phi 0, I mean if the shift makes sense, so if this is an integer, and 0 else. And this is again a slicing, so now we had to define these slices for any real number, which we did. So this is a slicing of D. Only that here, only in discrete, I mean in the integer values of this difference here, the categories are something interesting. Whereas in the general setting of slicings, a priori the p phi's can be non-zero for all values of phi. Okay, so this is going from torsion theories and T structures to slicings. You can also go the other way around. So conversely, so start with a slicing of A, and just I mean we've done this for the case of sheaves on curves. Pick any little phi between 0 and 1, and define T to be this category, and F to be this one, and this is a torsion theory. This is how our motivating example for the abstract notion of a torsion theory. And similarly, if now I have a slicing of D, and I pick up, continue in red, pick phi any real number, then I define D smaller than or equal to 0 as the subcategory. So I didn't explain it, but I hope the notion is clear. So for any interval, this is this full additive subcategory of objects whose semi-stable factors, these AIs, have phase in this interval. So that's the same notion as we had in the abelian case, now just applied by analogy to the case of arbitrary slicings. This defines a T structure, a bounded T structure, so there's a very unfortunate clash of notation. There are two things. First of all, I use weak inequality here and strict inequality here. This somehow you could, I mean, I could use weak inequality here as well, but so this is just a convention. But the thing that can't be avoided is that I have a smaller here and a bigger here. So that's and this has to do that if I shift this by 1, then I get everything in degree minus 1 or less. So so this then defines a T structure on the on the on the triangulated category, but moreover, the heart, its heart. So so this T structure has a natural heart, inherits a slicing by saying that the slicing in A for any phi is definitely getting this wrong, is the slicing of the triangulated category. The slicing of the triangulated category phi plus 1. No, sorry. Sorry. This is the heart. This is the heart, and the slicing then, the slicing P of. Getting confused with the colors. In the slicing of the abelian category, A now is given by the slices that live in this interval, so phi plus phi. So this is in the category D. I mean, the.
No, these are different forms.
And so now you can make this into a proposition, what was suggested already, namely that that a slicing of a triangulated category of a triangulated category D, they are in bijection with bounded T structures plus the slicing of the heart. And the way you do this, so you take a slicing of the triangulated category, so the phi here is just any real number. I pick this little phi to be just 0, so I define the heart of the abelian category as this abelian category plus the slicings and those I only have to define between 0 and 1. So it's not quite enough to give a slicing of the heart. You also have to know that the heart is actually that the abelian category is actually the heart of a bounded T structure. Okay, so this formalizes everything we have said about the p phis for the case of coherent sheaves on a curve. But in the slicing, we've completely forgotten about this function z that was defined in terms of degree and rank. And this comes in now, namely when I want to avoid examples like this one. The first example up there, this was an example of a slicing where the slices, the p of phis, are only additive categories and not abelian. And we definitely would like to have abelian categories as in the case of curves. So so this is part 2, stability conditions eventually. And roughly we linearize slicings. And you can do this in two ways. You could either start with the slicing and then try to find the function z, an analogy to the one that we've worked with on curves, or you could start with the function z and then try to define these slices. Okay, so let me first fix a few notations. So again, well, let me do this first on the abelian category, and then I later color this in red when I pass to the triangulated category. So A again abelian, and a stability function on A is a linear function Z from its Grothendieck group to C, and I want this one condition such that for all non-zero objects in A, this thing is contained in the upper half plane where I allow the it to be negative real. The stability function, so this is just a linear function on the Grothendieck group. I say this is compatible with a given slicing of the abelian category if for all E and P of phi the value of E is up to a real constant given by the exponential of the phase. So this is so before for the slicing, these were the slicings were given by these rays here, or visualized by these rays, and adding the stability function just allows me to put points on these rays for all the objects in the category. Okay, so and having this, so having not only a slicing but also a stability function compatible with it, one concludes immediately that the slicings are actually abelian. So exercise: if a slicing admits a compatible stability function, then the slices P phi are actually abelian. And the idea really is, if I draw the image of an object E, and I have a short exact sequence like this one, even when they say they're all semi-stable, so all contained in some slice, in general I cannot determine, for instance, the phase of the one in the middle by the phase of the outer objects. But if I have this linear function, then I can, because then the vector E here will be the sum of the two, and hence I can compute, well, I know that the slices of E prime and E double prime determine the phase. I'm sorry, the phases of E prime and E double prime determine the phase of E. Okay, so now you can define what a stability condition on A is. Stability. On an abelian category. So this consists just of a slicing and a stability function. So this is a slicing of A. This is a compatible stability function. And then that would be a nice notion, but if you try to build up the theory, then you soon need a certain finiteness condition, which I'll explain maybe later, not today. So this is a finiteness condition. Let me just say it implies the existence of finite Jordan-Hölder filtration. Remember yesterday I said, well, there's the Harder-Nusselmann filtration, but there's also the Jordan-Hölder filtration. Here, as I mentioned, I'll write down in a second, there's the notion of the Harder-Nusselmann filtration. This is this is in the definition of a slicing, but a priori we don't have finite Jordan-Hölder filtration, and this finiteness condition is slightly stronger than requiring that there exists Jordan-Hölder filtration. In these abelian subcategories. So that means every object in here, which we call semi-stable object, can be filtered by sub-objects such that the quotients are simple or minimal, meaning that they do not have any non-trivial sub-objects themselves. Okay. So now let me do the same thing for triangulated category, and you see that I just can use the same definition. So if I look instead at a triangulated category, then I also say that a stability function on D is a linear function from its Grothendieck group to C, and this condition doesn't make any sense here. So this I would take out for triangulated categories because I always have, for instance, for a linear function that if I take any non-trivial object and I add its shift by 1, the value, because of linearity, the value will always be 0. Okay. So this condition doesn't make any sense, but the next condition makes perfect sense. So I can define a stability condition on a triangulated category. Similar to the one before, and again there's this finiteness condition, which actually boils down to one for abelian categories. The difference here is that this exercise doesn't really make any sense. The abelian category, the p phi's are still abelian, but this picture doesn't really make any sense as soon as the phi goes beyond 0, 1. No, the p phi's are not the hearts. The heart of the T structure is given by the p of an interval. And in this interval, the slicings of the abelian category are just given by the slices of the triangulated category.
But all the same, once you have a slicing, you do have a heart, and why don't you then require this z of the heart lands and
Which is this condition?
yeah, well, you crossed it out.
No, but it comes again here. Okay, so there's one modification which you wish to do as soon as you realize that this K group can be rather horrible in general. So the K group of an abelian or triangulated category, even for a smooth projective variety over C, the K group, so K of x, which is the same as K of co-x or K of dbx, this is a finished thing that can be very large. And so infinite rank and nothing nice. So you it's often useful to allow only stability functions of the type that factorize over a fixed finite rank quotient. So this is a fixed finite rank quotient, and you require that that you only allow stability functions that factor over this a fixed quotient. So the most popular choice is the following. So the most popular choice is the numerical Grothendieck group. So suppose the category D is of finite type, which means that for all objects E and F in D, the space of morphisms between E and all shifts of F is finite dimensional. Oops, not zero. Finite dimensional, and then you can define the pairing between E and F, just the usual Euler-Poincaré pairing, as the alternating sum of the X groups between E and F. And so this is a bilinear form because this is linear in each of these terms. I mean, the usual thing, the Euler characteristic for long exact sequences is linear. So this gives a bilinear form on the K group, and you can, for instance, take gamma to be the numerical K group, meaning you divide out by the annihilator of this bilinear form. That is one choice. For instance, if you do this for D of a smooth projective variety, then what you find is what's called the numerical K group or Chow group of the variety. So then we have K of dBx, which is K of x, and here's the numerical Grothendieck group just defined. And if you map, for instance, the Chern character into the algebraic homology of x, so all the classes that are algebraic, so maybe I twist by Q here, then this one is a quotient of this one, and is expected by one of the standard conjectures to be an isomorphism, and in particular you see that this one has finite rank. So it's finite dimension.
I'm confused about why this gamma is always.
It is not always finite. No. I can take this gamma. That's the natural quotient which I might take, and here I'm explaining that in the geometric situation it is actually a finite rank because it's a quotient of the cohomology.
What is an example of set in this?
Say again?
An example of set of the function set in this?
Where's the function z? Oh, well, I haven't given you any example yet, except the one for curves we've seen. So that will be the topic of tomorrow's talk when we talk about stability conditions on surfaces. Right? So the only example for valid z you've seen so far is minus degree plus I times the rank. Okay, so now let's, since we started out with curves, why not looking at curves again and try to classify all stability conditions on curves. Oh, sorry, maybe I should have said, if I take this construction here, then one talks about numerical stability conditions. So these are the stability conditions where I require the z to factor over the numerical Grothendieck group. So these are numerical stability conditions. Okay, so stability conditions on curves. So this is due to Bridgeland and Macri. So we fix a smooth projective curve over some algebraically closed field, and we assume its genus to be positive. Now I'll point out where this assumption comes in. And then their theorem is that if whenever I have a numerical stability condition condition on DBC. So again, DBC always stands for the bounded derived category of coherent sheaves on C. Then there exists a phi in R such that its heart little phi is actually the abelian category of coherent sheaves on Z. I haven't had the time today to define the GL2R action, but usually some of you would phrase this theorem by saying that the space of stability conditions on C is a simple orbit of the GL2 plus R tilde action. I haven't defined what this thing is on the right hand side and how it acts on the space of stability conditions. And essentially, it says that up to this action of some natural group, the only stability condition on the bounded derived category of sheaves on a curve is the one that we've started with yesterday. Okay. So, but for this theorem, I don't need to know what the GL2 plus action is. So it says one of the hearts. I always have the choice where I put the heart, but there's a choice. So for one phi, the heart of the stability condition will be the abelian category of coherent sheaves. And let me try to give an idea of the proof. So tomorrow we will see, for instance, that this is never the case for surfaces. Once I pass to dimension 2, you can show this. So on a smooth projective surface, no stability condition will have as its heart the bounded derived category of coherent sheaves. Okay, so proof has 3 steps. The first step is a general remark on derived categories of coherent sheaves on curves. Every object in the bounded derived category on a curve is actually isomorphic to the direct sum of its cohomology sheaves, which I can write like this. This is the first remark. The second, and this is where the fun is, you show that all points and all line bundles, so this is a C, and all line bundles on the curve are sigma stable. I'd like to say something, or if I don't do this today, then I'll start with this tomorrow, because I really want to show you how to compute in these tildes of these categories. But suppose we have 1 and 2, then we can go on step 3 and observe that for any point in C and for any line bundle, there's of course a homomorphism. Well, there exists always a non-trivial homomorphism from a line bundle to the skyscraper sheaf, to the point sheaf in any point. Okay, so that means the space of homomorphisms is non-zero. But by step 2, both sheaves are stable, and that means the phase of L has to be smaller than the phase of Kx. Right? Because both are stable, so there cannot be, if the phase of L were strictly bigger than the phase of Kx, there couldn't be any morphisms from L to Kx. If the phases are the same, then there can only be an isomorphism between homomorphism from L to Kx if it's actually an isomorphism. Okay? So hence the phase of L is strictly smaller than the phase of Kx. On the other hand, I can use a Sergiality and just find that also the x1 from Kx to L, so this is dual, is non-zero, so which I write as the homomorphisms from Kx to L shifted by 1. And the shift of a stable object is always a stable object. So again, I have 2 stable objects. The phase of this one has to be smaller than the phase of this one, or equal, but then the objects are the same, which is absurd. So this one gives that the phase of Kx is smaller than the phase of L shifted by 1. But this condition I'd first forgotten says that the phase of L shifted by 1 is actually the phase of L plus 1. So what I find is that phi of kx minus 1 is smaller than phi of L is smaller than phi of kx. And if I put this as my little phi, then I see that for all points and all line bundles, that all point sheaves and all line bundles are objects in this part of my stability condition. And you know that every sheaf on a curve can be filtered with quotients either line bundles or point sheaves, and that means that the abelian category of coherent sheaves is contained in this abelian category. And in general, if you have two T structures whose hearts are contained in each other, then they're actually the same. Okay, so that means there's a little phi, sorry.
What breaks when the genus is not?
Well, this is in here. I'll start with this tomorrow. So it has to do with the fact that I want a certain homomorphism in one direction to be non-trivial, but I only know that there's a morphism in the other direction. And for positive genus, I can always multiply a morphism with a section of the canonical bundle, and it's still non-trivial, and then I can dualize and get to the one in my direction. So that, yeah, but I better postpone this to tomorrow. This will be a bit technical, but on the other hand, this is where the fun is, where the computation is, and if I don't do this, then it doesn't make any sense to talk about stability conditions on surfaces. So I stop here. Thank you.